So we've been in previous videos talking about functions. So we're going to do a quick, we've been talking pretty generally. We're going to do a quick tour of some of our typical functions, ones that we'll see often and want to be pretty familiar with. Again, this is made with the expectation that you're familiar with these. If it's been a while, I would suggest doing some deeper research using an old textbook, other videos that are out there. All right, so the most typical function, I don't know if that's true, the most typical, but usually the first function we encounter is what we call a linear function. So a linear function is a function of the form f of x equals mx plus b, and then m and b are constants, meaning they are, oops, that should be m and b are constants. Let's do are constants. And one thing we want to remember about them, so you might remember their slope and intercept. I'll remind us what that means in a moment. But a lot of the functions we have, we write them in particular forms, and there are certain constants in that form that tell us something about the function. And what we're really looking at here is a family of functions. This represents an infinite amount of functions, in fact, depending on what are the values of m and b, right? So for instance, f of x equals 2x minus 7, and g of x equals negative 1.7x minus, let's make it plus 19. Those are both linear functions, right? They both have a constant in front of x, and they both have a constant added or subtracted to x. I like to think of it as just added and one's adding a negative. So these are both linear functions, and the m and the b tell us which particular one we're looking at. So let's talk about what m and b are, and then take a look at some graphs. So let's start with b. That's an easier one. B, and just to be clear, the letters I'm choosing here, m and b, are just the traditional letters for this. There's nothing really magical or important about using these two letters. What's really important is we know when we talk about b, what I really mean is the constant, the thing that's added or subtracted to the x, and then m is the number being multiplied by x, right? That's what's really important. So b, the constant, oops, let's go back to black. B is what we call the y-intercept. Okay, so remember when we talk about graphs of functions, we use this opportunity to remind us of a few other things. Intercepts, whatever our graph looks like, right? So there's some arbitrary graph. Whatever our graph looks like, let's remember a couple of things. Each point on here is an input-output pair, right? So if this is a function, let's say h of x, this graph, each point is a value x, and the output for that value x, right? So the y-intercept is the place where, or the vertical intercept is the place where the graph hits the y-axis, right? It's always going to have the coordinate 0 for the x-coordinate, and whatever our function is evaluated at 0, right? So in the case of a line, f of 0, if f of x equals mx plus b, f of 0 is m times 0 plus b, or just b. This leads us to the idea that the intercept happens at the point 0, b, right? That's the input-output pair where it hits the y-axis, right? There's only ever going to be one of those, right? Because it has to have the input 0 and there's only one output for each input with our function. While we are looking at this, let's also note that a graph can have x-intercepts or horizontal intercepts. These are the places where the graph hits the x-axis. As seen in my sketch, there can be multiple versions of, or multiple instances of this. These all have the y-coordinate 0, and the x-coordinates are the x's that solve this equation, right? Where is the y-coordinate? What inputs lead us to an output 0? There might be one, there might be none, and there might be an infinite amount. There might be many, anywhere in between, right? So we can have lots of different of those. That's just a reminder. We're not looking deeply into that at the moment. So that's what our B value is. It tells us where we hit the vertical axis. M is what we call the slope. Okay, so there's a few ways we think about the slope. So I'll remind us what we probably have seen before. You might see delta y over delta x. This is a really good notation to get used to as we're prepping for calculus. This means the change in y over the change in x, right? Which means if we have a graph that goes through 2 points, like x1, y1, and x2, y2, we take the difference in the y coordinates, over the difference in the x coordinates, okay? And it gives us a number, it's a ratio that tells us how the y value changes as the x value changes. More specifically, if we change, let's be even more specific. If we increase x by 1, y changes by m, right? So that's what this slope number tells us. So in these functions up here, let's in fact do one of these. This first one I had, our example, f of x equals 2x minus 7. The y-intercept, the vertical intercept, is -7, because if I input 0, I get 2 times 0, or -7. This means the graph of this has to go through the point 0, -7. And let's look at that slope. Let's compute 2 values. Well, we just computed f of 0. Let's see if we change, if we increase x by 1, f of 1, we get 2 times 1, or 2 minus 7 is -5. So we increased x by 1. It looks like we've increased y by 2. Let's just do it one more time to be sure. So again, we've increased x by 1. F of 2, we got 2 times 2 is 4 minus 7 is -3. We're increasing y by 2 again, right? So that's what that slope tells us about a line, how the input changes as we increase, how the output changes as we increase the input. So let's look now at graphs of these linear functions. So again, this is probably familiar. Here's the simplest linear function, I think. This is the case where m is equal to 1 and b is equal to 0. So it goes right through that origin. We can see, as I said a moment ago, if we increase, let's go through that same idea. If we increase x by 1, y increases by 1, right? So we go from the point 0, 0 to the point, 1, 1. Sorry, I'm using 2 different softwares to draw. One writes on the paper, one will annotate the screen, and they write a little differently, so it's hard to jump between the two. So we don't have to be so rigid on increasing by 1. I think it's a nice, simple way to think about it. In this case, also just tells us a ratio. So when m is equal to 1, we're saying whatever we increase x by, y will change by the same amount. In this previous example where m was equal to 2, if we increased x by 7, y would increase by 14, right? So that ratio will hold. That's actually really the prime characteristic of a line, is that ratio holds true for all values. All right, so let's get an idea. There we go. Of how these values, what happens when we change these values. So here's my m at 1. If I increase m, right, what do I mean? I mean a change in x, an increase in x leads to a larger change in y, right? We get a steeper line, increasing by 1 instead of increasing y by 1, now increases it by 6.8. So we go up a lot more for the same amount of change, right? If it's negative, of course, that means as we increase x, we decrease y. And so we get a negatively sloped line. And there, right in between the positive and the negative, we get a 0 slope, right? If I change x, nothing changes about y. In other words, x doesn't have any effect on y, right? So there's our slopes. Here's our vertical intercept, right? So bigger and smaller, we slide up and down this line. Here I go changing the slope again. We can still increase or decrease the slope and the intercept. So here's the one we just looked at again a second ago, 2x minus 7. Almost off our screen. So it's going through the y-axis, the vertical axis down here at 0, -7, and increasing. Every time we increase x by 1, y increases by 2. Okay, so that's our linear functions. I won't say anything else about them in this video. Hopefully these are things we've seen before, and it's not too much of a review. Let's jump into quadratic functions. So quadratic functions are a little more complicated. So in a quadratic function, there's a couple of ways we can write a quadratic function. So let's start with this. F of x equals a x minus h squared plus k. Here, a, h, and k are constants. Okay, so let's talk about what these constants do. So, well, we'll just go through one at a time. A, so let me just make them clear here. Here's A, here's H, here's K. A gives the direction and let's say width. Let's put this in quotes. I don't know if I have a better word for this. Now I'll give more examples of what this means when we look at the graph. I just want to get these ideas down. This gives the direction or the width of the graph. And then the graph, let's say it a better way. And then the point HK is the vertex. Of the graph. Okay, so let's look at a picture of this graph to talk about what those things are. So let's start with f of x equals x squared. This is the case where a equals 1, h equals 0, and k equals 0. Okay, so it's kind of our simplest case, right? We need here for a to not be 0. That's the only limit on that constant. If it's 0, we don't really have a quadratic. We'd end up with a horizontal line. Okay, So let's look at a picture of this. So, yep, we got it set up right. So here is this graph, right? We've probably seen this before. We get a parabola. So I said A gives the direction. So this parabola right now is opening up, right? Meaning it has a minimum point and then it extends upward. If we change and the width, right? So this is kind of the standard width when A is equal to 1. Let's see what happens as I change A. As I change it, right, making it bigger, my graph gets a bit skinnier. We can think of this in two ways. It's either compressing the graph horizontally or stretching the graph vertically. Most people find it, I think, more intuitively to think A stretches it vertically. If I make A smaller than 1, it starts to get wider. There's 0, where it becomes a flat line, no longer a quadratic. And then negative, here's what I mean about the direction. If it's negative, this parabola points down. Instead of having a minimum, it has a maximum, and then every other point, the vertex, every other point is below that maximum, right? And this one is at 0, 0. And that leads right into the vertex. The vertex is that maximum minimum point, the turning around point of the graph, right? And we can see this right in the form of the equation, right? If A is positive, x minus h squared, the smallest this can be is 0, because if x is bigger than h, we're squaring a positive number, it's going to be some positive number. If x is equal to h, it's 0, and 0 squared is 0. And if x is smaller than h, we get a number minus h is negative, but we squared it, becomes positive. So this thing here, the thing that gets squared, is either positive or 0. It's never negative. If A is positive, that means this whole front piece can never be less than 0. And so the smallest this function can be is whatever the value of k is, because as you increase or decrease x from that point, the squaring keeps it positive and the values begin to grow. If A is negative, it just flips all of that logic around, right? So now let's see what happens when we change h and k. So I said that the center, the vertex is at the point hk. So as I change h, I'm changing the x coordinate of the vertex. And if I change k, I'm changing the y coordinate of that vertex, right? So now I have a different family of, again, like the linear functions, we have a family of functions here. All these different parabolas are examples of quadratic functions. And so regardless of whether it's opening up or down or how wide it is, I can move the center around, the vertex around to determine that maximum or minimum point, right? This is also an example starting from f of x equals x squared, adding in, so let's do one here. Let's put a equals 2, h equals 3, and let's say k equals -2, right? So this is the graph I have here, is equivalent to doing the following transformation. So there's a nice reminder about transformations. If I took f of x and rewrote it, or didn't rewrite it, I'm creating a new function that I multiply f by 2. I'm going to, what was h? Was 3, and then subtract 2 from the whole thing, right? So look at what this does. I take 2 multiplied by f of not x, f of x minus 3. So if f of x is x squared, this is x minus 3 squared, and then I'm subtracting 2 from the whole thing. That's the graph that I have right now. It's a transformation of our original function, which started right there. It vertically stretched it. It shifted it 3 units to the right and shifted it 2 units down, right? So just a quick, this just comes from, if we start with the function x squared, we can use transformations to see how these a, h, and k values affect our function, right? Transformations are another great thing to remind ourselves of. It's also the case that we don't always write our quadratic functions this way. We can take this function, f of x. So let's start new. So I'm defining f of x as a times x minus h squared plus k. I can expand this thing. So if I square this, I get x squared minus 2hx plus h squared plus k. I then multiply through, distribute that a, I get ax squared minus 2ahx plus ah squared plus k. So this is looking ugly, but if we remember, everything here is just some number, and everything here is just some number. So if I just call, these are just some numbers. I'm just going to give them a new name. So if I take b to be equal to negative 2ah and c to be ah squared plus k, I'm writing this quadratic an equivalent function written in a, in a different form, right? Some people call this the standard form. So let's just take a look at this. So here's the case where a is 1, b is 0, c is 0. So that's again just f of x equals x squared. But as we change a, it has a similar effect. B and c still raises it up and down, but moving b around does kind of odd things to it, right? It's not as straightforward, which is why we have these two different forms. This form of ax squared plus bx plus c is handy in some cases, adding and subtracting quadratics with each other. Sometimes that's just how you get it. It's easier to deal with sometimes, but having it in what we call the vertex form, that was this first form I showed you, is really nice because you know exactly where the vertex is. It's not impossible to find it in the other, using the other method, using it from this other form. We'll talk about that in a second. But they are the same functions, or the same family of functions, just different ways to write it. And so depending on what we're doing, we want to be able to work with both of them. So we just saw how we can convert from one to the other. Let's do an example of that with the one we were just doing. Oops, there we go. So we had this g of x was equal to 2x minus 3 squared minus 2. If I wanted to write that in an expanded form, I would have 2x squared minus 6x plus 9 minus 2. I get 2x squared minus 12x plus 18 minus 2, 2x squared minus 12x plus 16, right? And this would give us the exact same graph. So let's in fact see that. Let's change these values. Let's change a to 2. B is going to be I need to make this go down to negative 12. Negative 12. And C needs to go up to 16. And let's compare that to, so it might be hard to see, there's a subtle color change going on. The green one is the one we just graphed in standard form. The purple one is the one we had in vertex form that I've just shown that they're equivalent to each other, okay? So that's an easy way to go from, it's easy to go from vertex form to standard form. It's probably worth knowing how to go back, and how we go back is by using a method. If we want to go the other way, if we're given something in standard form, suppose we're given a function like this, and we want to write it in vertex form. There's a few ways we can go about doing this, finding the vertex is one option. I'm going to use a different one only because it's a nice thing to demonstrate, which is completing the square. Okay, this is going to be a trick that seems like maybe it came out of magic, but it's a nice thing to know. All I need to do is justify each step as I go. At the end, you'll see maybe why I did these steps, and we can have a longer discussion on that some other time if anybody's ever curious about how we got to all these things. So the first thing I'm going to do is I'm going to factor A out of the first two terms. So remember, we're assuming A is not 0 because we have a quadratic, right? So I left a space there because we're going to do something in a minute. But notice if I multiply A back in, I've got ax squared plus bx plus c. So I haven't changed anything. Here's the mysterious part, the really mysterious part. I'm going to take half of this b over a. So half of b over a is just b over 2a, and square it. Didn't quite leave enough room. Let's clean this up a little bit. Okay, right? Now, if I just add a number to this function, it's not the same function anymore, but I can fix that by subtracting the same number. So what have I actually added? I haven't just added b over 2a, all of that squared. I've added that multiplied by a, because if I distribute all of this, if I distribute a, there's a factor of a on that. So whatever I add to this thing, I have to subtract. So I'm going to subtract a times b over 2a squared. Okay. All right, now, why did we do all that? Well, the reason we did this is because it makes what we have in here a perfect square. If I write x plus b over 2a squared, that's equivalent to what I have up above. All I've done is factor, and you can see that for yourself if you multiply everything out, right? That was really how why we did what we did up here, right? Our goal was to make it a perfect square. And I'm just going to simplify what's going on back here a little bit. Let's write this as a. So if we simplify all this, we'll have a b squared over 2a over 4a. Right? I just squared that quantity and canceled the factor of a. Again, a is not 0, so I'm comfortable having it down there. Well, notice right now, let's do one more thing, actually. Let's rewrite this in an odd way. Yeah, 4ac minus b squared all over 4a. So I just gave them a common denominator. Notice what I have here now. I have a times a quantity of x minus some number plus some number, right? There's a bunch of constants floating around, but if we call these constants, so I can rewrite this as a times x minus h squared plus k. Here, h is equal to negative b over 2a, and k is equal to 4ac minus b squared all over 4a. Bring that up a little bit. Okay, and so we get back to our vertex form, and something nice shows up. Let me make this a little cleaner. It's hard to tell my h's and b's apart. Let me just write this a little more nicely. This was h is equal to negative b over 2a. This is something many of us remember. This gives us the x coordinate of, oops, b should be a capital here. The x coordinate of the vertex if you're given a graph in standard form. And so we're allowed to just use that. We don't have to go through this whole process each time. But I think completing the square is a nice process for anybody to understand. It's where the quadratic formula comes from, which I will not go through at the moment, but it's worthwhile to remind yourself how to come up with that formula. It didn't just show up out of thin air. And I want to mention one last thing. We've looked at linear and quadratic functions. These are both examples of a larger class of functions called polynomials, which are sums of constants times powers of x, typically positive integer powers of x. And so, just trying to think if I've ever seen it defined as anything but that. As far as I know, everybody defines it that way. You can write something with non-integer powers of x, but I don't think anybody considers this polynomials. I've never seen a space for that to be important. Anyhow, sorry. That's where we're going next. So these are the first two examples of something called polynomials. So we're going to see where these fit into this larger category. These are the two most common, the ones that we see most often, but we'll see all kinds of polynomials in different forms moving forward. Okay, that is it for this one. Thanks, everybody.